So the next thing we'd like to talk about here is regression when x is a binary variable. So x is going to be a variable that's always 0 or 1. This is actually a fun example, breaking x into just an indicator of two different categories or two different factors that you might have in the data. It's fun because it's actually a step back. It's a simpler thing than what we were just doing a moment ago, which is the general version of OLS. So, okay, the idea here is if x is 1, you have one set. In this California school data, I have small class sizes. And when x is 0, you have the other set. We're going to use one variable to indicate the 1 or the 0 to basically split the sample into two factors. If you have three factors in the data, you're going to need two binary variables. And if you have four factors in the data, you could break up all of the data using three binary variables. Another example would be x is equal to 1 if female, 0 if male. The default way of coding these, by the way, is you would name a variable something like female, and then 1 would be true and 0 would be false. If you do it the other way around, people are probably going to get a little bit confused. You might also have a variable like treatment or treated in something like a controlled trial for a new experimental medicine, in which case the treated group would have a binary variable equal to 1, and the control group would have a binary variable equal to 0. Again, if you have more factors, you can use a couple of different binary variables as long as you have one less binary variable than the total number of factors you want to represent. As you see here, this variable 1 and 0 is going to correctly split things into two groups for each of these three cases. All right, so a single variable. Binary regressors are sometimes called dummy variables or just binary. Usually beta 1 in an OLS regression model is the slope of the line, and that is still true here, but the picture becomes very, very simple. So let me go ahead and grab the pen, put some axes up here on the board, and I'll give you a scatter plot of dots. All right, this is what we've been doing so far. As usual, I draw it so that it looks like it goes through the origin, which it does not need to do. But you have the slope of the line here. We've got rise and we've got run. And then beta 1 hat is going to be rise over run. So let's say A over B. And we'll express the model as yi is equal to beta 0 plus beta 1 xi plus some error term, which I usually call epsilon I, and is u in the slides. Okay, then the fitted value is going to be yi hat. Yi hat is the actual line, so yi hat is equal to beta 0 hat, the estimated number, plus beta 1 hat plus, sorry, no plus, xi. And no error term here because the fitted model has error terms equal to 0 on average. So yi hat has an interesting name. We call this the expected value of yi conditional on xi. That means you tell me what x is, and I will give you my best prediction for y. The expected value here is the conditional mean of y, so my prediction should be off by 0 on average. Sometimes the point comes in a little bit above the line, sometimes the point comes in a little bit below the line, but if I add up those vertical distances for every point, they add up to 0. They're 0 on average. Okay, so that's very handy, but you plug in an x here in order to get your predicted value of y. Let me give you another one. Come over here, draw the exact same picture, but what I'm going to do is I'm going to go ahead and say I know something about x down here on the horizontal axis. It's binary, so it's always either equal to 0 or it's equal to 1. And I've done something a bit silly. I've made it so that the y-axis is not lined up with where x is equal to 0, but I did that for illustrative purposes because what I'm going to do is I'm going to draw the data for x equals 0. Watch. On the vertical axis, I've got a scatter plot of points here. Several of them. They kind of just look like a mess, but fair enough. And then in the sample where x is equal to 1, I've got another set of points. Okay, points, 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 points. All of these have x equal to 1. What's the difference between this picture and what we had on the left? Well, what we had on the left, x takes on many different values. I trace all of these points down to the horizontal axis, and I see that all of these are happening. X could be many different things. Over here, x is always either 0 or it's equal to 1. And I can still fit a line to this data, no trouble at all. What I'll find is the line goes here through the point that represents the average expected value of y given x equals 0. The average of the y's where x is 0. So this is, in fact, take all of those points where x is 0, get the average, and it will go through that point. Then over here on the right, guess what? Expected value of y given x is equal to 1 is going to be this point right here, which perhaps looks like I should have had a few more points up there so it looks like the average, but that's where the line is going to go. It's going to go through this point over here, which is the average of y given x is equal to 0, and it's going to go through this point over here, which is the average of y given x is equal to 1. Now notice what happens. Draw the box, okay? Talk about A, talk about B. Rise over 1. Run. Beta 1 hat is equal to A over B. Let's talk about A. What is the vertical distance between this point and this point? Well, on the axis, trace back, that's the expected value of y given x is equal to 1. And on the axis down here, it's the expected value of y given x is equal to 0. So A is the difference between those values. If I find that people in this group are taller, well, this is their average height. And if I find that people in this group are shorter, well, this is their average height. And the difference between those average heights is the rise. Okay, so that'll be A. Let's talk about B. What is B? In this case, B is the horizontal distance between these 2 points, x equals 1 and x equals 0. So I suppose I don't have to tell you that 1 minus 0 is equal to 1. The change in x on the horizontal axis is simply 1, and the change in y on the vertical axis is the difference between these 2 groups. So it comes out, with b being equal to 1, that this is just the difference between the expected value of y in the group where x is equal to 1 and the expected value of y in the group where x is not equal to 1, which implies that it's 0. So it's just the difference between 2 groups. This is amazing. So we can also do this with t-tests, and we've seen in Excel that there are a couple of functions in the data analytics toolpack that will do the difference between 2 groups, a simple difference in means test. But OLS is going to nest that functionality here in the case where x is a binary variable. So this is extremely helpful. Let's talk about the model very quickly. Back to here. And what we've got is, here's your model. yi is equal to beta 0 plus beta 1 xi plus your error term, which is 0 on average. When xi is 0, the xi right here is going to drop out of the model, and it's going to give you, no beta 1. That term will drop out. You will have yi is equal to beta 0 plus an error term, which is 0 on average. Okay, so the average of yi is just beta 0, hence beta 0 here. When xi is equal to 1, yi is equal to beta 0 plus beta 1 plus an error term, because the xi in the original model is equal to 1, so the beta 1 doesn't drop out, but the xi is equal to 1, so it simplifies, and you can write it more simply this way. And then the expected value is beta 0 plus beta 1. So when I estimate the model, I'm going to have an expected value of beta 0 plus beta 1 in the case where xi is equal to 1, and I'm going to have an expected value of simply beta 0 in the case where xi is equal to 0. Well, take the difference between them, and immediately you will see beta 1 is equal to the difference between these 2 group averages, or the difference between these 2 group averages is equal to beta 1, precisely as we have here. All right, fair enough. That means when I interpret the coefficient in an OLS regression, using a binary regressor, I can just interpret that coefficient as this group has on average this much more for whatever their outcome variable is. ANOVA is a set of terms that I am not particularly fond of, analysis of variance. It's sort of a hodgepodge. It's a catch-all phrase for a bunch of different things, including several of the difference in means tests. So the 4 different difference in means tests, the t-tests and the z-tests that we have in Microsoft Excel, would be called ANOVA. But there's a lot more that falls under that category, or that basket, that header of things that we would call ANOVA. So what we are doing right now is actually ANOVA, talking about the difference in means between a couple of different groups. And then there are some other things that we might lump into that category. Just throwing that out there. Here's the simple example from the regression of test scores on class size. Now, we saw this in another set of slides. If I split everybody up based on their class size, and I say there's one group where the student-teacher ratio is small, the average in that group is 657.4. Okay, the standard deviation is 19.4, and there are 238 observations in that group. If I use the other group as large student-teacher ratio classes, so anything that's not less than 20, let's say, and there is a typo in the textbook on this, by the way, the average in that group is 650. The standard deviation is 17.9, and there are 182 of them. Take the difference between the two groups, which you could do by scratch, or from scratch by yourself, instead of using OLS, or instead of using the difference in means test in Excel, you'd come up with 7.4. Then the question is not, is there a difference? Because of course there's a difference, right? These data are always going to include some amount of noise, as we like to imagine that the data are sometimes sampled from a population in a way that gives you a sample average that is not perfectly equal to the population average. So it's possible, even if there was no relationship between student-teacher ratios and test scores, that I could get 2 samples and they would have different averages. But that average should be close to the same if there was truly no difference between these groups and I had large enough samples. So the question is 7.4 a meaningful number in the statistical sense? Now, on this test, 7.4 may be a meaningful number in terms of the outcome, but the question is that more than a couple of standard errors so that I can treat this as a statistically significant result and say it's not just noise? There really is a difference. And the formula for the standard error of the difference in means is this thing here, right? So you come up with the variance for the small STR group, and you come up with the variance for the large STR group. Divide each of those by the number of observations in that category, add them together, and take the square root of the entire thing, which is easy enough to do, but it's a formula you have to remember as far as the difference in means test is concerned. It might be advantageous if I can do this entire thing. First of all, if I could just have Excel do that for me, that would be wonderful. Or if I can call this entire exercise a very simple regression problem, which, you know what? I think it is. So the average for the small STR group would be the average for the large STR group plus whatever the difference is. So if I make a dummy variable d that is equal to 1 for the small group, then I have this model that nests both groups, and I can estimate that model using ordinary least squares. Hopefully, using ordinary least squares will give me the same answer to the problem. Spoiler alert, it will. So let's pop over to Excel. And what do we have? I've got the California School District data here. I'm going to go ahead and scroll a little bit to the right, and I'm going to create another column. So I've got reading scores, math scores, there it is, student-teacher ratio. I'll go ahead and make a variable called small, and I'll use the if function here. So if checks whether a condition is met and returns one value if true and another if false. So let's say if the STR for this observation is strictly less than 20, then return 1. Otherwise, return 0. And so for this first observation with an STR of 18, this should give me a 1. And then for the second observation with an STR of 22, this should give me a 0. Let's see. Beautiful. I'll send it all the way to the bottom. And just to check, I'll say equal to sum of that entire column. I'll go ahead and add up the whole column and see how many there are. 238 observations fall into the small category. Well, good. It looks like I made a dummy variable that correctly identifies the 238 observations in this small category. What will I do with that? I'll go ahead and run a regression treating this binary variable as x. I don't need this 238 anymore. Let me go up to data analysis. Notice here are the 4 difference in means tests that I was just talking about. But let's do regression for now. Hey, not bad. Okay, all right. So, okay, that I won't do that. I'll do input y range, not test score this time. Yes, actually, test score. Test score will be perfect. Let's do that all the way to the bottom. Good, good. And input x range, let's do small. So, small, all the way to the bottom. 420 observations. Perfect, beautiful. I did include the top row, so I will leave labels selected. New worksheet is fine. I don't need a line fit plot, although, you know what? It doesn't hurt anybody. Let's send it. Here's my beautiful picture. As you see, I've got x equals 0 over here and a whole bunch of observations. And on the vertical axis, the average of that group is predicted here. I have a whole bunch of observations over here where x is equal to 1. And on the vertical axis, I see that their test scores are represented, and the average of that group is represented here with the 657.4 and a more or less 650 on the vertical axis over here on the left. So that's perfect. It's a bit prettier in some ways than the picture I drew, but I'm partial to my own art skills, so thank you, Excel. Thank you for that. Then let me zoom in and see what else it has to say about this. So interestingly, R squared tells me that whether this district has a small or large student-teacher ratio actually explains not quite 4, we'll say 3.6 or 3.7% of the variation in test scores, which is quite an interesting result on its own. Now that's a pretty small number compared to 100%, but it's not small when you consider that all I've done is split these into 2 groups. All right, so intercept, we'll call it 650. The difference between the means, we'll call it 7.4. The standard error for that we'll call 1.8. The t-statistic here, we'll call it basically 4. And the p-value needs to be less than 0.05 in order for me to reject with 95% confidence the null hypothesis that, in fact, there's no difference between the school districts with the small student-teacher ratios and the large student-teacher ratios according to test scores. But that's not what I see. I see 0.0000752. So a very small, very small p-value. I reject with 99.9% confidence the null hypothesis that this is actually 0 in the population. There's no difference between the small and large STR school districts for their test scores. Well, there you go. The 7.4 is just the difference in means, and the 1.8 is just the standard error. Divide the difference in means by the standard error, and you've got a t-statistic, which we know how to handle now. I will say one other thing about this. If I go all the way back to the original data, so I made a binary variable here, but let me pop open that data analysis toolpack again. There is, if I want to get the exact same thing using one of these t-tests, 2 sample assuming equal variances is the one that will do that. Now, the way Excel does the standard errors for ordinary least squares does assume that the variance is constant across the entire picture. So the way I've drawn it here, you will see very conspicuously I've made this sort of try to look like a tube. It doesn't have any additional shape to it. Parallel lines all the way through. All right, the variance is the vertical distance, and I've made it try to look like it's the same in every case. Over here, I may or may not have succeeded in doing that with these points that I drew in. I made it look like the group on the right perhaps had a little bit higher variance, which turned out to sort of resemble the picture that we saw when Excel plotted this for us. Well, you do get the option. With ordinary least squares in Excel, it will only give you the formula for standard errors that assumes that they all have the same variance. But for the t-test, you have a choice. I'll do the one for equal variances just to confirm for my own purposes that it does the exact same thing as regression with a binary variable. So I'll double click on that. I have to pick some variables, variable 1 range, variable 2 range, and then hypothesize the difference between them. The way this is supposed to work is I'm supposed to select the test scores for each of these groups. As you see, I've got a whole bunch of small and large groups all mixed together here, so it's difficult to do that. I'll go ahead and pause that for a second, and I'll come back up to small. Sort the data by small. Smallest to largest will be perfectly fine. And then I've got all of the small school districts ordered first. All right, now we can do two sample, assuming equal variances. I need test scores all the way down to, I believe, row 183. Looks like I already practiced this. Let's see. The last 0 over here, test scores in row K. Sure enough, that's 183. And then if I go 184 down to 421, that will be the rest of the data. Hypothesize no difference between these groups. And hit OK. What comes out? The average for one group was 650. The average for the other group was 657.4. It gives me the variances for each of these two groups. It gives me the number of observations in each of these two groups. And what would you do with that? Well, you could plug that into this formula if you were so inclined, and you could crunch it out with your calculator to get a standard error of 1.8, which is what Excel is doing here. There's my t-statistic on 418 degrees of freedom, and it gives me a p-value for that t-statistic one-sided test, a p-value for a two-sided test, which looks a little bit more like what we just saw in the regression output, and it gives me critical values for the t-statistic here. So that is excellent. If you want to do the exact same thing, assuming unequal variances, you will get a perhaps more robust, slightly different number for the standard error. All right. The t-statistic is going to be based on that standard error as we have over here. Notice left to right the logic flows. So once you have your coefficient, and then you calculate a standard error, you can get the t-statistic by dividing the coefficient by the standard error or subtracting a different number from the coefficient first if your hypothesis is that it's something other than 0. So the coefficient will not change if I use the other tool here, to sample assuming unequal variances, but the standard error will change, which means the t-stat will change, and once in a blue moon, this could affect your decision making, right? In general, if you're going to test whether two groups are different from each other, I strongly recommend this one here, assuming unequal variances. There's no reason to believe that the variance in both groups is the same if you're testing whether the mean is different. Why should I think that the rest of its properties are all the same? Go for this one every time. This one will produce exactly the same thing as the Excel regression output does, but I encourage you to use this one. Anyway, we'll pack that up and pop back to here. What else do we have to say? Quick summary. Beta 0 is the mean of y when x is 0. Beta 0 plus beta 1 is the mean of y when x is equal to 1. So, of course, the sort of treatment effect, if you want to call it that, the difference in group means is beta 1, the slope of the regression line, and also this difference in means, if you want to do that and test things using the simple ANOVA. Standard error is the usual sort of thing, and the t-statistic is the usual sort of thing. So if you understood these from the other videos, nothing really special is happening here. Slightly different statistic because we fed it slightly different data, and that's all it is. There is a topic hanging here, heteroskedasticity and homoskedasticity. A moment ago, I was telling you that the variance of these two groups may or may not be the same, and that you should never assume that they are the same because there's just no reason to do that. Well, Excel does use standard errors for ordinary least squares that are based on the assumption that the variance is the same all the way across the sample, hence this picture where I tried to emphasize that fact. And I'll do it again. This variance over here on the left looks about the same as this and about the same as this. Contrast that with, for instance, if I had drawn a picture like this and said, here are the points, and then they get increasingly spread out as you move to the right, in which case I might fit multiple lines to it like this and say that the story varies depending on where you are in the distribution. That's where the logo that I use on all of my stuff comes from. So if you're seeing that and saying, "Oh, that's what that is." Yep, correct. It's a bit of a niche topic, not one that comes up a lot, but one that I like to research and one that can be very interesting and useful in a lot of different contexts. Here's a simple picture of what we might model heteroskedasticity looking like. Hetero means different, skedastic means the distribution. So this is a different way of saying it might be heteroskedastic, as I just drew here. And here's a data set that you will recognize. You'll say, oh, that's the NLSY data that he showed us in class the other day. It's actually not. It's the same variables from a different surveys from the CPS, the current population survey. But as you see, it's exactly the same story. The more years of education you have on average, I predict that you're going to earn more money. But the top of the distribution seems to be moving up at a much faster pace than the bottom of the distribution. So it's possible to get a bachelor's degree, a master's degree, or a PhD, and then wind up making not very much money, depending on perhaps what topic you chose to study. Whereas some of these people up here, the payoff for those additional years of education is very, very steep, as you see, if I were to draw this picture again. All right, but OLS is capturing the average across the entire group. If you want to, you can control for what major they are or what program they're in, and you'll start to tell a different story that might be more nuanced. If I don't control for that, I just get the average across the entire group. Okay, fair enough. The class size data I'm not really worried about too much. It doesn't really look like a tube, but it doesn't have that characteristic fan shape like we have here, so I'm not worried about it too much. If you are worried about it, draw the darn picture. So here's your famous acronym, and this is extremely helpful in data analytics. Draw the picture or plot a scatter plot. Just look at the data. Look at the data, and all of the mysteries will be revealed unto you. If it looks like this, you say, hey, I think I can fit a line to that. I notice that there's a lot of variation. I'm not surprised then if I have low fitting power, very low R squared, because this data simply has a lot of noise when I only have student-teacher ratio as an explanatory variable. Or here, I see, okay, well, it still doesn't look like a huge amount of explanatory power, but the heteroskedasticity is very apparent in terms of the variation that we have for these highly educated people on the right-hand side of the sample. Heteroskedastic, maybe homoskedastic. All right, draw the darn picture. Okay. One of the nice things about assuming that the data are homoskedastic is the formula for the variance simplifies in this way. And you'll see the variance of beta 1, which is just the squared standard error, right? Looks like this. Sigma squared of the error term, the variance of the error terms, divided by n, how many observations you had, times sigma squared of x, the amount of variation in x. Found another typo. Okay, so there are three magical things. Very important to know each of these. The noise is the variation in the error terms. This is a great picture because it's actually quite a lot of noise, right? That's what I'm saying. These error terms spread out a lot. X only goes from here to here, but there's a lot of noise. So that's noise. The variance of X is essentially signal. So the variance of beta 1 hat has this story about a signal to noise ratio. More noise gives you larger standard errors, which is bad. More signal gives you smaller standard errors, which is good. And of course, more observations, more n, means smaller standard errors as well. which again is good. Turn that into some more pictures that we can draw. Well, I'll give you a couple examples of what this might look like. If, for instance, these are the data, I've tried to draw it so that there is in fact an upward slope. But you know what I've done? I've given you a lot of variation in the vertical dimension here, which is noise, and not so much variation in the horizontal dimension here, which is signal. So if I say, is that the true regression line, or is perhaps this, or this, or this the true regression line, it's difficult to tell, which is why we have a larger standard error when we fit the data to fit a line to this data. If I turn that around and I give you, say, this data. Well, look at these observations way out on the right and the left. They have massive explanatory power. I've given you a larger variation in the x dimension. So that's this term here, the variance of x. I've also given you smaller variance of the error terms. There aren't any points way up here or way down here. So I've given you low noise and high signal in the red dots compared to the black dots. This is great. I would like to see more variation from right to left. That does create a couple of interesting conundrums where, for instance, I could give you an outlier in the x dimension, this point right over here. Well, it's an outlier apparently in both the x dimension and the y dimension because it doesn't look like it's anywhere close to the line. But what's going to happen with this point being all the way down there by itself, because it is so far out in the x dimension, it actually has more leverage to move the line. An outlier here might drag the entire line down, but you see, I'd have to move the line relative to every other point in order to move it, like this point and this point and this point would have larger error terms, which means that this point is not going to do much to move the line. The one way out there on the right, though, I could keep the line in almost the same spot, but just change the slope, right? Just move the slope a tiny bit. And it's now a bit closer to this without being much further from these. So a point way out in the x dimension has more influence on the slope of a line, and we call those leverage points. That's another thing to look for. We've got heteroskedasticity, we've got outliers perhaps in the y dimension or in the x dimension way over here. The outliers in the y dimension are going to move the line because of course they are. But outliers in the x dimension are going to change the slope of the line, and the further they are out in the x dimension, the more power they have to do that. So we call them leverage points. Once again, draw the darn picture. Look at the picture, and if you see a scatter plot with points way out there in either the x or the y dimension, you might want to be concerned about whether those points are anomalous in some way and whether they have undue influence on the rest of the shape of the relationship that you're estimating. That shows up on the homework as well. All right, so these three things, the noise, the variance of the error terms, the signal, the variance of x, and then the size of the data set, which is n. I always emphasize those are the three things, even in the formula we saw earlier that was a bit more complicated because we hadn't assumed homoskedasticity. It's really the same things and maybe a little bit of a fourth one that has to do with the shape of the data, whether it looks like this or perhaps like something else. But that's outside the scope of this course. I always make a joke about this because I tend to write them on the board and then circle them. And if I have 1, 2, 3 red circles, it starts to look like the State Farm Insurance logo, which I guess I haven't put in these slides, but it's funny to me. This text is stolen from the nice textbook by Stock and Watson, so I've highlighted it here just to tell you that this, all right, if they're throwing shade at somebody, this is actually from Stock and Watson. Some people, example, Excel programmers, find the homoskedasticity only formula simpler, but it is wrong unless the errors really are homoskedastic. All right, well, no hard feelings towards Microsoft, but they do raise a valid point. This number is perhaps not the best number that I would want to see. It's maybe not the perfect standard error, but it's going to be close, and it's going to be workable. and we're going to run with it as long as we're in Excel. And if you switch to something like Stata or R or Python or choose your favorite statistical software, you will have the option to implement the so-called robust standard errors, which don't care about heteroskedasticity. All right. In summary, does our regression analysis using the California dataset answer this question convincingly? Whether new teachers are hired so the student-teacher ratio falls by 1 student per class. What is the effect of this policy intervention on test scores? This slide is basically to pump the brakes. So what I've determined here is I have descriptive statistics. I can tell you the difference in the means. I can tell you the mean test score for each of these categories of school districts in California. I have predictive analytics where I can predict what will happen if I give you a school district and say the student-teacher ratio is this. Can you tell me what the test scores should be? And I can do that either by splitting them into 2 groups and giving 2 different predictions based on whether you're in a group, or by fitting an entire line to the data and you tell me exactly what the student-teacher ratio is right here, and I'll give you a prediction right there. Right? So this is a bit more information than just 2 groups. But can I make policy intervention prescriptions using this data? That's sort of a higher standard. You can choose your own adventure here and decide whether you think hiring 1 more teacher per student so that the student-teacher ratio falls by 1 student per class. Okay, well, I think it would have an effect. I believe it would have an effect. I believe that this would be good for the students. The data doesn't tell me that, all right? So the data tells me the raw correlation. Districts with low STR tend to be ones with lots of other resources and higher income families. This is true. There are other reasons, there are other stories that you can tell about why the students in the low student-teacher ratio districts might be doing differently from the students in the high student-teacher ratio districts. And so simple regression, where we only have 1 variable here, is probably not the way that we should approach the problem. I do have data on a variety of other factors that I could try to bring into the equation and control for some of these other things. All right, so I've got grade span, I've got enrollment total, teachers, something about who's eligible for meals, number of computers, test scores, computers per student. Expenditures per student is probably enormous. Average income in the district tells me a lot about the families of these students, or at least their incomes, and so on and so forth. Other factors are going to be important. But we've got a good start here. And at the very least, I can tell whether this group has a different set of outcomes than that group, even if I can't tell necessarily why that is. The exact same tools that we used in this video will be useful in a variety of business scenarios. So for instance, if you're working in retail and you wanted to test whether your sales numbers are different on weekdays than they are on weekends, which of course they probably are, you would use either a difference in means test, or you could use a binary variable for whether a given day is a weekday or a weekend day, combined with a data set on sales numbers for many different days. And you could easily test whether you do in fact have different sales on weekends and weekdays. Finding that you do, you would be able to make business decisions based on that. And quantifying how different those are, you would be able to say, well, I need more people working the store on Saturdays, or I need more of some other input in your production in order to try to maximize the outcome. So that's it for this video. I will see you in the next one.